Hey everybody, welcome to this tutorial. We're going to be going over set and reset functionality with TIA Portal. We'll be using Factory IO to simulate a conveyor that has two brake beam sensors. And then we'll also be talking a little bit about interacting with Factory IO in a more practical or in a more detailed way than we have in the previous videos. So I figured we'd start off with Factory IO. If you've watched the first videos, you should be familiar with how to set up Factory IO to talk with Siemens PLC, so I won't be covering that again. Here, I want to focus primarily on the interface for Factory IO. So up at the top, we have the pause and play buttons. These basically turn the simulation on and off. And then the other thing that we have here is that we have a time scale simulation. So if we have particularly long processes or we want to emulate something or simulate something running for multiple hours at a time, the time scale functionality is something that we can use. We can also use time scale to really slow things down as well if we need to. By default, when you turn it on, it's going to have anything like you can do like 10 times as slow, or you can do essentially 4 times as fast. That's your range. You don't have like real discrete timescale operations here, so you can't type in like 1.5 or something. So you're doing either half speed or 1/10 speed, or you're doing 1x, 2x, 3x, 4x normal speed. And then over here, these are our camera modes. So normally, by default, you're set up in orbit. And the orbit camera works. You can zoom in and out by scrolling on the mouse wheel. You can also orbit around your focus point by holding down right mouse button on PC. And then if we want to change our orbit point / our focus point, we can double click anywhere in the environment. And so, for example, if I double click right here on the corner of this component, double click there, and I begin rotating, you can see that white orb has shifted focus or shifted its point, and we are now orbiting around a new point. So that's how the focus, or that's how the free orbit camera works inside of Factory IO. So just to review that real quick, if you want to orbit around that point, you hold down right click. If you want to zoom in and out, you use the mouse wheel. And then if you want to change the orientation of the camera or the focus point of the camera, you double click anywhere in the space to have the camera center on that area and orbit around that area, like I am doing now. There's one other thing that I forgot to mention. You can also pan this camera by holding down the center button on your mouse and moving the mouse around. And this actually changes the location of your focus point. You can see that that's been moving around when I do that. Okay. The next thing that we have is the fly camera. And that camera utilizes WASD. So just like in a video game, if you're a PC gamer, but you can move about and you can orbit and you can basically kind of fly around wherever you would like in that orientation. The mouse wheel changes its behavior from zoom to, I guess, what you would call it elevation. If you scroll up and down, so scrolling down, you decrease in elevation, scrolling up, you increase in elevation. You still use right mouse to look around. And then if you want to like go higher, you can just look up and hold down W. So if you're unfamiliar with the WASD format of control, you're going to place your middle finger on the W key. Your ring finger is going to be on the A key. Your index finger will be on D. And then A and D, they are forward, left, and right, respectively. So W is forward, A is left, D is right, and then S is backwards. And so with those three, or with those four keys, those give you your four kind of cardinal directions that you use. And then holding down right key, you can move the camera independently of that to create more complex motion. Okay, the last camera mode is first person. And if you've played first person games before, it behaves exactly in the same fashion. You're tied at a specific vantage point, and you can walk essentially around a machine or an object and go upstairs and that type of stuff. So those are the camera modes. I'm going to switch back to free orbit here. You can also use WASD in free orbit mode to pan as well. Here, you can switch camera. You can have pre-saved camera positions, so you can snap between different locations. So if we go here, go here, go here, there are some defaults that are always preset for every scene in Factory IO, so they can be helpful for getting the correct vantage point that you're looking for, getting back to a view of the machine. You can, over here is sensor tags. So this is actually particularly useful if you're exploring a scene. You can turn sensor tags on and off, and you can see that the names of those sensors are hiding and then becoming visible as I do that. The same is true for actuator tags. So anything that is essentially an output in Factory IO is called an actuator. And then you can also hide and show the palette window. The palette window is really only used when we build or modify a scene. We'll get into that probably in a later video. For right now, this is just kind of a tutorial on the basic movement of Factory IO. Okay, so now that I've gone over that, we're going to start transitioning into programming this scene. I do want to point out that all of these scenes in Factory IO, they have pre-built information for us. If we click on the scene icon here, it'll pop up a web page, and they have all of the scenes listed out that are pre-built to use. I'm currently looking at the set reset, and these pages typically just have a link to a YouTube video that shows us the functionality of like what the system is supposed to do from the Factory IO perspective. In some cases, we'll be doing exactly what's demonstrated in the video. In other cases, we may deviate from that slightly. Okay. The other thing that I would like to point out with Factory IO is the parts page. If you are interacting with any of the scenes, all of the scenes are built using these Factory IO parts that have characteristics kind of pre-programmed into them. I think the thing to keep in mind here is that when you're looking at more complex systems, it can be helpful to have specific information about them. So if you go and look at the machining center, what it looks like is that they have a tag table that kind of summarizes the outputs and the inputs that are associated with that. And then we can use that information to, from a programming sense as we go through the thing. And it has descriptions of what each of those do and how the robot cell, in this case, or their machining center works. Okay, so let's go and actually look at this system in the driver, from the driver perspective. So I'm already talking to PLC Sim. But just really quickly, if you have set up your PLC like you have in the previous tutorial, to utilize your the I/O that's associated with your with the Siemens 1512C-1 PLC that we're using, we will need to add an offset for the I/O points. So the offset that you will need is on the input side, you will need an offset of 10, and on an output side, you will need an offset of 4. We're going to take a quick look at what that actually means. So I'm going to minimize factory I/O, maximize our PLC here, and if we go into the device configuration, or there we go, device configuration here, and if we double click on, if we go to one of our digital input modules and we click on I/O tags, you can see that because of the way these modules are configured, this is the second module in this stack associated with this PLC. Its I/O starts at input 10.0 by default. And these are the tags that are associated specifically with that module. If the orientation of these modules changes, or if you're making modifications to the system, like you're adding additional modules, it can be much better to create tags inside from the device view under the I/O tag table than it would be to just go to your general tag table here and start adding tags as normal. So if we go back to the device configuration real quick, you can see that if I'm looking at the I/O tags for the entire PLC right now, you can see everything get listed out in terms of their addresses according to the I/O that's there. So if we click on this first module, we can see that this is an analog input module. It has 5 analog inputs and it has 2 analog outputs. All of these inputs are addressed as input word 0, 2, 4, 6, and 8. And then the outputs are QW0 and QW2, respectfully. These are the I/O addresses that we need to map to if we're going to access these in factory I/O. What that means is that when we open up factory I/O and we do this offset, we are configuring the I/O that's in the scene to basically line up with how our modules are addressing them internally. Because by default, if we go back to our configuration real quick, and I say that there's 0 offset, which is the default setting for many of the scenes. This all updates live, by the way, so you don't need to hit like save or anything. You just go back. You can see that the default setting here is 0.0 and 0.1. Well, if we go and look at that on the PLC, we don't have a 0.0 or a 0.1 on any of our modules. So we have input 1 or input 10.0, input 10.1, input 10.2, and we have input 12.0 and input 12.1, right? And then here, these are words. They're not strict Boolean inputs, so they work off of a different thing. So we need to be able to align these types of things up. So that's what the offset in factory I/O is meant for, is to make sure that your I/O addresses are from the factory I/O side are aligning with the I/O addresses on the PLC side. If those get misaligned, your simulation is not going to work correctly. So we need to make sure that that happens first. Okay. So now that we've gone over that and I have this already set up, we're actually going to start programming here. And so our objective is basically to emulate that functionality that we saw in that short video about this scene. So we have a conveyor that's going to start automatically, which is our entry conveyor. You can see here that it has this exclamation point. If we hover over it, we can see that it's forced true. So this is just going to turn on automatically when the simulation starts. And it's simulating like an in-feed into a process. And then we have sensors A and sensors B that are both currently true. If we look at these with the PLC tags, stick this in the lower right-hand corner, I think. If we look at these, we can see that sensor A is the first sensor, sensor B is the second sensor, and then we have an output that is our conveyor. You can also see here that as I'm clicking on these names, I'm adding these to a visible tag table that's on the left. And when this is simulating, when this is running, we can actually see the state of these IOs change accordingly. So now that we have, now that we're kind of set up there, let's go and actually start setting up our program. So for here, we're going to, since this is a conveyor system, and this is going to be pretty straightforward, for this exercise, we're going to do all of our programming in main OB. In future videos, we'll get into some more program organization stuff, but here, this is going to be much more focused on just like the actual logic, using the logic. So what we're going to do at this point, the first thing that we're going to do is we're going to actually set up our tag table. You can import the tags if you would like. I'm going to go through and manually add the tags because I think this is a really good habit to get into. You're not always going to have a pre-built tag table for your machine that you need to program. So we're going to go into device configuration, and I'm going to go to the second module, which is our DI DQ module right here. And I'm going to go to the IO tags table, expand that a little bit, and we're going to start adding our inputs here. And so we're going to create our sensor A, sensor B, and then we're going to have an output that is our conveyor. And in this case, by default, these are being added to the default tag table. I think it is really important that when you are working with specific components or multiple inputs and outputs from different types of machinery inside of a system, those should be broken out and organized into their own tag tables, ideally. This is a relatively small project, so it may, like, we could technically just leave everything in the default tag table and this would not be an issue. But I want everybody to get into the habit of adding specific tag tables for either components or to separate input and output. So with that in mind, we're going to create a tag table. I'm going to just call this the conveyor. And in this conveyor, with this conveyor added, instead of going back and adding stuff here directly or going here and like maybe copy pasting or something like that, that can get cumbersome. The most efficient way I've found to place these tags in their appropriate tag tables is to go back to the configuration menu. And here from this drop-down menu, we can just select, now that we've created that extra tag table, we can select the tag table we want those associated with on a per module basis. So that's going to make organizing our IO much simpler. So this is now, if we open here, we can now see we have these tags associated with that tag table. So now we're just going to upload. This is the first time I'm connecting to my PLC in this project, so I'm getting that warning. We're going to load that. And then the next thing that we're going to do is we're going to go into main OB, and we're going to begin programming. So this is going to be an exercise using set and reset. So here we're going to have a network that's going to control our output. And then we're going to, and this first network is going to be this first network is going to actually turn our conveyor on. We're going to use the set command. So here, if we click on the drop-down menu for our output module, we're going to hit S for set. This is going to be our conveyor. So the easy way that we can get access to those tags, if we click there, if we click on the tag table, you can see in the detail view that those tags populate down here, and we can simply just drag and drop from this menu right here. So if sensor A, under this circumstance, if sensor A is true, we are going to, or the input is high, I should say. If the input is high, then we're going to set the conveyor. If we look at that, by default, that's going to turn our conveyor on. In reality, what should be happening is that our conveyor should only be turning on when we've detected the presence of a box. So if we, what this logic should actually be should be inverted. And so now when the sensor breaks, what's going to happen is and we lose that high signal from the sensor, that's when we're going to set our conveyor high. And then the next thing that we're going to do, our next network, is going to contain the other functionality that we need to look at. And we're going to set another output, normally open. This is going to be sensor B, or excuse me, that was an input. We're going to set this to a reset. And this is going to be the conveyor as well. Now, if we do this, this might be like our first, everybody thinks that this is like the first way to do this, right? There are a bunch of different ways that you can implement this functionality. And technically, what we are doing, in my opinion right now, would be considered this wouldn't be best practice in terms of the way that we're organizing this program, but we're just focusing on the logic. So if you've seen other content of mine that says that we should be breaking this out into functions and all of that type of stuff, yes, we absolutely should be, but we'll get to using functions and building up the organization from the project a little bit later. Again, right now we're just focusing on the logic here. So now that we have our program written, theoretically what should happen is that when we lose this sensor here, or when we lose the signal from the sensor, i.e. the box breaks this beam, we're going to get a signal that's going to set the conveyor high. And the set function, what it does is it just says, like, once this rung goes true, it turns this output on. And it leaves it on until we receive the reset command down here. This reset command could be issued right away under some circumstances, depending on the machine and the context. Other times, it might run for hours before we actually need to send the specific reset command. That just depends on the context of the equipment and the process that's being programmed. So this reset command, the thing that we need to understand about set and reset is that set is going to turn something on and leave it on, and reset is going to turn something off and leave it off. However, the caveat is that the reset command is only going to take effect if it has an associated set point as well. So if we leave this, if we were to do something like this, this would not be a valid use of the reset command because we can't reset a conveyor, or we can't reset this output if it has never been set previously. So set and reset always get paired together. Okay. We'll need to compile our program. Blocks were successfully compiled, and we'll need to load that into our PLC. Hit load. And then let's see where we get to. We're going to go online with our PLC, and we are going to monitor this logic. And let's see what happens. Come over here. We'll hit play. So we're getting some interesting behavior right now, right? Set and reset are both active simultaneously. Okay, so we have a situation where our logic is not working as expected, and the first thing that we're going to do here, I've reset this. I'm going to run it again, and we can see that things are not working correctly. We know that this sensor is being tripped because we can see that its activity has changed over on the left-hand side, but we are not seeing any change in logic here. And additionally, we are not seeing any change at our tag table. You'll remember previously I was talking to you guys about making sure that your tags line up. Well, I foolishly forgot to reset after I showed you what the default state was here. So we need to add our offsets back in of 10 and 4. And then we're going to change that back. And you can see that the moment that I did that, we started getting some change in behavior here. So we're going to do sensor here. Factory IO running will be there. Conveyor will be our output. And let's go back here. We'll stop, reset. And that conveyor turns on. And that conveyor turns off. If we reset that again, we can watch the logic. There's our set signal. And here comes our reset. Boom, just like that. Now, there are a couple things here that we should also do to enhance the reliability of this conveyor program. The first thing that we really want to be thinking about is that each network or rung that we are programming really should be as unique as possible from all of the others. What we're looking for is to define only like explicitly unique states that certain things happen in. We'll talk about this in more detail as we grow in complexity here. But best practice at this point would be, in my opinion, is that we're going to add some additional logic here. We're going to add 2 outputs in each of these. The order of them doesn't matter. This is just a stylistic preference. And under our PLC tags, we are actually going to say that sensor, for the first state here, sensor A must not be true, and sensor B must be true for us to set the conveyor. And then sensor B must not be true, and sensor A must be true to set this conveyor, or to reset the conveyor here. So this explicitly excludes the possibility of other scenarios where these sensors may trip independently when we don't necessarily want them to set and reset the conveyor. So if we run this again, we'll upload this. Oh, I forgot to do one quick important thing. Whenever we make program changes like this, we need to make sure that we compile first, and then we send our upload, load. There we go. And now we can hit play. First state trips. You can see how the logic is building here. And then sensor B trips, boom. And these two states are completely divided from each other. So they cannot, there isn't an opportunity where somebody could potentially interfere with the process, or this helps prevent unanticipated events being injected into a process that causes behavior that we don't want. So that is our solution for this first programming lesson. If you guys have questions, reach out to me. Do this a couple different times, and then we'll start talking about some more complex programming in the next video.